Hello, ladies and gentlemen. Let's talk this time about the Bronsted Lowry definition of acids and bases. In 1923, two chemists, one Danish, one English, independently came up with a more full and complete understanding of how acids and bases worked. One was Johannes Bronsted, the other one was Thomas Lowry. And up until this point, back in the 1800s, we've been using the Svante Arrhenius definition of an acid and a base. Arrhenius said that acids increase the concentration of hydrogens, bases increase the concentrations of hydroxides. Well, you've got to understand that science is going to evolve, and science is going to evolve as our understanding evolves. In the 1800s, the nucleus, the neutron, the proton had not yet been discovered. Science came a long way in the 50 years between the Arrhenius definition and the Bronsted Lowry definition. So there's always room for improvement in science. One of the big challenges in acids and bases was understanding things like ammonia. Ammonia is NH3. And when you mix it with water, you get ammonium hydroxide, NH4OH. Now, most of the other bases that were out there, sodium hydroxide, magnesium hydroxide, these things already came with their own hydroxides. But ammonia all by itself was a base. And chemists didn't understand, what do we do? How do we come up with a better definition of what makes an acid, what base makes a base, beyond just the 50-year-old definition? So this is the Bronsted Lowry definition of an acid and a base. Put a little star by this and that. The Bronsted Lowry acid says it's a compound that donates hydrogen. And a Bronsted Lowry base is a compound that accepts hydrogen. So it's based totally on the hydrogen ion moving, swinging between one compound and another. It is just whether that hydrogen ion is being given or it is being accepted. Now, Bronsted Lowry acids are things that donate hydrogen. So for example, hydrochloric acid, when you put it in water solution, it is going to break apart, give a hydrogen to water, and make hydronium ions. It donates a hydrogen. If you have a base like ammonia, it is something that is going to accept that hydrogen ion. So it takes a hydrogen ion from the water, takes it, accepts it, and makes ammonium ions. So if something accepts a hydrogen, it's a base. If it donates a hydrogen, it's an acid. Big important idea is this: acids produce hydronium ions. Put a little star by this. It's a big deal. In aqueous solutions, it is hydronium ions that we count, that we actually, when we get to the point that we start talking about pH, pH is based upon how much, what's the concentration of hydronium ions in a particular solution. So hydronium ions are a big deal when we start discussing acids and bases. Now, why do hydronium ions get produced? Well, it has to do with the polar nature of water. The water, if you remember, a polar molecule is one that's not the same from one side to the other. Water molecules have these two unpaired negative electrons out and in the front of it, and that leaves the front of the water molecule kind of negative, the back of the water molecule kind of positive. And this polarity means that the water molecule, even though it is a neutral charge, it still has this ability to electrically attract other things, including a stray little hydrogen, and it can pull this hydrogen away from things like a hydrogen chloride ion or atom. It can pull it away, attract it to another water, and make hydroniums. Now, when you start pulling hydrogens away from things, in Bronsted Lowry acid-base chemistry, they discovered that you end up with reversible reactions. Remember, in a water solution, the ions are always in motion. It's a big sock hop. The ions are swinging back and forth and changing partners, and it's a big dance. And the hydrogens can be lost and they can be gained by waters and acids and bases. So this reaction has this reversible symbol because these ions are constantly moving from one place to another. It produces things that are called conjugate acid-base pairs. And it works like this. If you have something like hydrogen fluoride or hydrofluoric acid is a Bronsted Lowry acid because it will donate a hydrogen to make a hydronium. It is a Bronsted Lowry acid, and it makes, when you pull that ion apart, it makes something which is called a conjugate base. Now that fancy name, and it means the leftover bits of this acid after it gives its hydrogen away is called its conjugate base. Now water, when it accepts this hydronium, it becomes an acid, and the thing that actually takes and accepts the base, this thing accepts the hydrogen, is called the base. But you're going, wait a minute, that's water, Mary. Water is not a base. Water is neutral. What are you talking about? You're making me crazy, lady. Well, water is a weird thing because water can be both a acid and a base. And we'll talk more about that in a second. Ammonium acts as a base when it gains a hydrogen from the water, and this is the base. Its conjugate acid is over here, and it is what is produced after that hydrogen has been accepted by the ammonium. Now, when the water molecule in this situation acts like an acid because it is giving away or losing a hydrogen to the hydroxide. I'm not going to ask you to pair up or work through an awful lot of these because, again, this is a basic chemistry class, but I want you to have heard of these so that when you go forth and go to the next level chemistry, you've heard of this. I do want you to understand this. Water is wacky. It is referred to as an amphoteric compound, meaning it can be either an acid or a base. Water can actually donate a hydrogen or it can accept a hydrogen. So water is pretty special. We're pretty grateful that it covers most of our planet. Some examples of these Bronsted Lowry acid-base reactions you're going to see in life. One is when you put lemon juice or vinegar on fish. If you go to a restaurant and you order fish, very often they're going to have a lemon wedge on the plate. And the reason is because a lot of people like that taste. Well, fish is a little bit basic and it's a little alkaline. And acids neutralize these bases. If you go to a British country, and I went to school in England, I have grown very fond of putting malt vinegar on fish and chips. It tastes really, really lovely. But the acids in these two solutions are going to neutralize that fishiness. It's going to smell less fishy, and it's going to provide a little bit of a sour tang, which is very, very tasty. Another example of a Bronsted Lowry acid-base reaction is pickling. Pickling, the vinegar in the salt solution is going to produce a situation where the pH is so incredibly acidic that no bacteria can live in that environment, and it's basically going to preserve the food a long time. But it also, along the way, produces an environment where good bacteria can live for a while and ferment the food. That's going to change the taste. Eventually, the acidity is going to get high enough that it's going to kill off all the bacteria, and you have pickles that can last for years on a shelf. A third and last example that you are going to experience of Bronsted Lowry acid-base reactions is pharmaceuticals. Now, many of the medications that you and I are prescribed are not water soluble. They are covalently bonded organic molecules. That means they are made of carbon and hydrogen, and they do not dissolve in water. Well, if you want to absorb them in the stomach, you want them to go through the human digestive system, you've got to do something with these so they are more easy for the human body to absorb. So how are these drugs treated so that the human body can accept them? They're very often reacted with a dilute or weak acid. Excuse me, diluted acid, not weak. I've got to say this correctly. And hydrogen ions in the acid make the medicine more water soluble and easier for accessibility within the human body. Here are just a couple examples. If you look at them, there are many, many others. Codeine. Codeine, that is a cough suppressant, cough syrup, and you can get Tylenol with codeine and things like that. It is actually codeine hydrochloride. That hydrochloride is added to the codeine molecule to make it more easy to absorb. Lidocaine hydrochloride. That hydrochloride is there again so it can be absorbed by the human body. Morphine is morphine sulfate. It is not a hydrochloride, but it is made into a chemical salt. Salt's easy for the body to dissolve and absorb. Hydrocodone, also known as Vicodin, is reacted with hydrochloride, making it something, again, easy for the body to absorb. So look at medications. Very often you're going to see an HCl or a hydrochloride or something like that. Part of the name, the purpose of that is for reaction within the human body. All right, folks, see you later.